So, as I mentioned before, when you solve that equation, or when you write out that equation, the determinant of sigma minus lambda I equals to 0, what you're going to get is a characteristic equation that'll have the form so this is called the characteristic equation. I already like this writing app better. It also has the other app. This is weird that nowadays they would even make an app but the harder I press, the harder the stroke, right? Just like a pencil would, right? So if I just barely press down, which gives a more natural writing on the tablet. Anyway, so you're gonna have this characteristic equation where the I1, the I2, and the I3 are called invariants. Invariants. And in our case, we're going, really talking about stress, so we might say invariance of the stress tensor. However, any matrix would also have invariants. Why are they called invariants?
They cannot be varied.
Varied by what? Like if I strain, if it's stress and I strain it more, does that mean that those numbers don't change? Invariant to what, I guess is what I'm asking. What have we been talking about today?
The coordinate system.
Yeah. So those coefficients, whatever they work out to be, are invariant to a change in coordinate system, right? Which becomes really useful in terms of constitutive modeling, right? Do you guys know what I mean when I say constitutive model? Okay. So I'll just take a little bit of an aside, and I'm going to do that, I'm just going to have to jump ahead a second, right? But basically where we're going with all this is we want to write down the engineering conservation equations, conservation of mass, momentum, energy, right? So, ultimately soon we're going to derive conservation of momentum equation that looks like this. So, again, I'm jumping ahead here, but just to make a point. So this is rho u, the u vector double dot, right? So 2 time derivatives, right? So what's 2 time derivatives of acceleration? Okay. So this is acceleration. Now that's density, but what if I multiplied right here by volume? What would the density times volume be? Mass. So on the left-hand side, I have something that looks like conservation of mass. I have something that looks like MA, right? Mass times acceleration. Right? On the right-hand side, this thing will ignore for a second, but same thing here, right? If I multiply by V here, so let's ignore that for just a second, and multiply by V here, these are body forces, so you could assume gravity, for example. So if I have V there, again, I have mass times gravity. That's a force, right? So I have MA equals force, right? Does that equation sound familiar? Yeah, Newton's second law, right? So what we're deriving and where we're going is the continuum version of Newton's second law, which includes internal forces, right? That's where this divergence of the stress arises. due to internal forces because that arise due to deforming some solid body, right? Not even a solid body. This equation also applies for fluids, as we'll see, right? So this is just the graduate school version of F equals ma, because F equals ma only works on rigid bodies, right? It's, you know, if I throw this pin across the room and I don't consider the fact that the pin deforms as it's flying through the air, then that's what F equals ma solves, right? But if I need something more, if I whack this pin, if I whack it like that and it flies across the room, how do you this is another aside, but if I whack this pin, and I'm sorry people listening on the video, you won't be able to see but if I whack this pin and it flies through the air, do you know how it actually, if you could like zoom in on it, the ends of it with a microscope, do you know how it actually flies through the air? Would you believe me if I told you that? The pin, so I whack the end of the pin and a stress wave propagates to the other end of the pin and it reflects. So the initial stress wave is in compression because I whacked it, right? I pushed on it. I hit the end of it, a stress wave propagates to the end of the pin, and when it gets to the end of the pin is free. There's nothing there. And so that stress wave will reflect in tension. So now a tensile wave is running the other way in the pin, and this end, when that happens, so I whack it, the stress wave, there's like a compressive wave here, it goes to the other end of the bar, the pin, and then this end of the pin moves like that. Tensile wave travels back down the bar, reflects in compression, and this end moves like that. So if you could zoom in on this pin, and you can actually, if you use like really high-speed cameras nowadays, you could actually see that this pin, if I whack it like that and it flies through the air, it moves like this. And that's how everything moves, actually. Any solid body, if you whacked it, there's stress waves that we can't see, but you can measure with strain gauges and other things, and that cause the dynamic motion like that. Most of the time we don't care, right? It doesn't really probably change the trajectory of the pin, where it's going to land over there on the other end of the room. But if the pin was made out of like some sensitive material, some very brittle material, graphene or something, then if I whack it, then perhaps, I said graphene. Graphene's not actually brittle, that brittle if it's in a single layer. But it's a ceramic. If I whack it, then I could overcome the internal stresses, and cause it to fail. So just simply whacking it could cause the thing to break, right? So unless I'm going to break my pin, I don't really care about those stress waves, and like it's not going to change the trajectory. But if I do care about the internal stresses and how it might, I say break, but also perhaps like permanently deform it, right? My pin wouldn't be very useful if it was like bent in half, So anyway, okay. So just back up a bit. This is the equation we'll be deriving soon. It's just F equals ma. But I want to solve this equation for displacement, right? I have displacements over here. They're unknown, right? I can measure the density. I can measure body force like gravity, right? But I need to, like right here I have stress, okay? And so what I need is something that relates stress to displacement. Some function that takes me from stress to displacement, right? Because if I have a function that takes me from stress to displacement and I plug it in there, then the only unknown in that equation is displacement, and I can solve it. It's a partial differential equation, assuming this is a function of x and t, right? This is a gradient with respect to x. Those are derivatives with respect to t. So it's a partial differential equation. And this thing right here is what might be called the closure law, right? It closes the equation so that we can solve it, right? In other words, we can't solve this equation right here unless we have a way to get stress into displacements or from displacements, okay? And that thing that we get, how we get from stress to displacements is called a constitutive model, right? Constitutive model. So, it's spelled like constitutive, and sometimes you'll hear people say constitutive model, right? And I mean, you've all seen this before, at least, you know, in the simplest case in one dimension, we just have that stress is Young's modulus times strain, right? And we already know that strain, in one dimension, is partial u partial x, right? So in one dimension, if I plug this relationship in there, then my entire equation is a partial differential equation in u, and I can solve it, right? It closes the equation where I can solve it. That's a constitutive model, okay? So in our case, something that, in this example, it's something that relates stress to strain, right? Darcy's law is also a constitutive model in the conservation of mass equation, right? It relates velocity to pressure, so that we can put the conservation of mass equation in terms of pressure, right? Pressure gradient. All right, so with respect to this aside with constitutive modeling and going back up here to talking about invariance, we would not want to have, it would not be a good idea to develop a constitutive model that, in fully in 3 dimensions, that is not invariant to a rotation. Because if you did that, it would mean like to populate that constitutive model, you'd have to go to the laboratory, do a test, rotate the sample an infinitesimal amount, do a test, rotate the sample an infinitesimal amount, do a test, rotate the sample an infinitesimal amount, do a test, and you spend the rest of your life doing that just to characterize one material, right? So what we would like to do is to develop constitutive models with respect to the invariance, and because those are invariant to a rotation, right? You'll get the same relationship between stress and strain no matter how you rotate it if you use the invariance. So what are the invariants? I1 is equal to the trace of sigma. And in additional notation, that is sigma II. And of course, because, so we can take, this is invariant, so I can take the trace of this unrotated stress, or I can take the trace of this rotated stress, rotate it into the principal coordinates so that I have the principal stresses on the diagonal. But if I take the trace, which the trace, sigma II is a repeated indices, so that means the sum of the diagonals, right? So if I take the sum of the diagonals of this matrix or the sum of the diagonals of the unrotated matrix, either one of those is going to have the same answer, right? That doesn't mean the individual diagonal opponents will be the same. They won't. But the sum will be the same, right? And so, in terms of the principal stresses, which is only sometimes useful, really, can be often useful in geomechanics because we often characterize the state of stress just through the principal stresses because it's pretty easy to figure out what they are and the directions. So in terms of the principal stresses, the first invariant is just sigma 1 plus sigma 2 plus sigma 3. Okay? But again, understand that you don't have to, it's useful to know what it is in terms of principal stresses, but you do not have to rotate the matrix you don't have to solve the eigenvalue problem rotate the matrix into the principal stress strain coordinate, and then sum them up. That's too much work. You can just sum up, however you have your stress tensor, if you just sum up the diagonal, you'll get the invariant. Right? So the second invariant is 1/2 sigma ij minus 1/2 I1 squared. Or in terms of the principal stresses, sigma 1 times sigma 2 plus sigma 1 sigma 3 plus sigma 2 sigma 3. So again, and using our initial notation, so we're going to sum over, it's a double sum here, so this results in a scalar value, right? Sum over I and sum over j. Right? And then this is just that I1. The third invariant is the determinant of sigma. Anybody know what that is in terms of the principal stresses? Yeah, just multiply them together, right? Sigma 1 times sigma 2 times sigma 3. How'd you know that? Linear algebra, okay. Yeah, so there's a rule in linear algebra, or you learn from experience, that any matrix, certainly any diagonal matrix, if the matrix is only diagonal, right, then what's on the diagonal are the eigenvalues, right? The determinant of any matrix is also equal to the multiplication of all its eigenvalues together, okay? But it also, the same rule applies, in fact, to any upper or lower triangular matrices. So if you have even if you had a matrix, you know what I mean by upper, so if you have a matrix U that's upper triangular, that means it has entries on the diagonal and above it, but zeros below. Any matrix that looks like that, or the converse, the lower where you have entries on the diagonal lower, then the eigenvalues of any matrix like this is just they sit on the diagonal, and so the determinant of any matrix like this is just the multiplication of the diagonal. In fact, in a computer, when you solve an eigenvalue problem, they often use an LU decomposition, right? So you can take any matrix. There's a set of operations that you can do to transform it into a lower diagonal matrix times an upper diagonal matrix. And in this case, the lower diagonal matrix actually has zeros on the diagonal and below it. And the upper diagonal matrix has, would then have entries there. And so you can basically then you can take the multiplication of the eigenvalues of the upper diagonal matrix, and that gives you the eigenvalues. So that's how a computer would solve an eigenvalue problem for like a large scale problem. Right? So there's another decomposition that we have. Sometimes we write the stress tensor like this. So this thing we often call the spherical part of the stress, or also the hydrostatic, sometimes the dilatational. Sometimes you'll see all of those words, any of those words. And this is called the deviatoric stress. And the deviatoric, so the spherical, the hydrostatic, the dilatational, that part of the stress is often called the pressure. And here I'm not talking about like a pore elasticity, pore pressure. This is a spherical or isotropic stress. You can see it just in the way it acts, right? So this is the sum of the diagonal entries times the Kronecker delta function, which can be thought of like an identity matrix, right? And then you're taking 1/3, it's like an average, right? So this is like the average hydrostatic stress that characterizes resistances to change in like pure compression or pure expansion of a material. And the deviatoric stress characterizes the shear behavior of the material. So that's another way to think of it. It's like this is a decomposition into the shear and the hydrostatic parts. And the reason that we often do this type of decomposition is because in plasticity, particularly in metals plasticity, we assume that metals undergo what they call isochoric deformation, which means that the volume doesn't change, right? So the first term represents volume change, the second term represents shape change, right? And when in metals, just due to the nature of how metals plastically deform, remember we talked about plasticity a little bit before. We're talking about like inelastic behavior or non-recoverable behavior. Think about a paper clip, right? If you bend the paper clip too far, it doesn't go back. You've plastically deformed it. And that is a result of you basically slip planes of any atomic structure. There's planes that are slipping over one another and piling up, and that's what causes that. And it's all due to shear motion, not due to hydrostatic compression. So what this means is, at least in theory, is that if I have a chunk of metal, I can squeeze it infinitely. As long as I squeeze it hydrostatically, uniformly on all sides, I can squeeze it as hard, I can put the entire weight of the earth into it. And I can squeeze it as hard as you could physically imagine. And when I let it go, it would spring back just like it was, in theory, right? Yeah. And for the most part, that theory works for metals. Metals typically just behave due to deviatoric motion, okay? That is not true of rocks. Rocks have pores in them, right? And that's why I say in theory, because there's, some metals have pores in them too, even if it's just accidentally in the casting process or something, right? So rocks obviously have pores in them. We flow water through them. We flow oil through them. So if you hydrostatically squeeze a rock, it will inelastically deform. You can crush the pores out of it, and such that when you let it go, it'll be in a smaller volume than it was before. Okay. So rocks have, can have pressure-dependent plasticity and shear-dependent plasticity, and we'll talk about that more when we talk about constitutive models for the failure of rocks, right? Because the constitutive model I presented earlier is like the simplest linear elastic constitutive model, but we need more sophisticated things to be able to model rocks well. Okay, so I think the last thing I'll just say then is that the deviatoric stress also has its own. So since I'm on another page, I'm going to say invariance of the deviatoric stress, and we typically use J for those. So the first one is 0. The second one is Sij, and the third one is the determinant of S. Okay. So again, you know, the deviatoric stress, you can also rearrange this equation, right? It's the total stress minus the hydrostatic part. So when you subtract off the hydrostatic part, then that leaves that the pressure is zero because you've taken it out. By definition of, you know, in the deviatoric stress. Another thing that we often call that first invariant of the stress tensor you know, this is like 3 times P pressure. Where again, I'm not talking about fluid pressure, I'm talking about a hydrostatic pressure in this, you know, that's related in the stress tensor. Okay. It's the hydrostatic part of the stress. That's what I should say. The hydrostatic part of the stress, the spherical part of the stress, the volume changing part of the stress. Whereas the other, you know, spherical, the deviatoric is shape changing. All right, we'll end there for today. Like I said, at the beginning of class, I know a couple of you came in late. I'll just repeat it real quick. Regular lecture on Tuesday, and then I'll be traveling, and I'm going to have to record a couple lectures. And what my plan is to add a little bit of material to those lectures to make up for